Hello everyone, this is Kinjal Parmar. Today we will discuss parity generator and parity checker combinational digital circuit. So let's start. Parity generator and checker. In digital systems, when binary data is transmitted and processed, data may be corrupted due to noise and altered from zeros to ones and ones to zeros. The parity generating technique is one of the most widely used error detection techniques for the data transmission. A parity bit is an extra bit included with a binary message to make the number of ones either odd or even. A parity bit is used for the purpose of detecting errors during the transmission of binary information. This additional bit, known as a parity bit, is used for error detection purpose, and using this parity bit, we make number of ones either odd or even according to the parity bit requirement of our combinational digital circuit. The message, including the parity bit, is transmitted and then checked at the receiving end for errors. An error is detected if the checked parity bit does not correspond with the one transmitted. So, the circuit that generates the parity bit in the transmitter is called a parity generator. The circuit that generates the parity bit is known as a parity generator. And the circuit that checks the parity in the receiver is called a parity checker. The circuit that checks the parity in the receiver is called a parity checker. So here we design parity generator and parity checker for odd parity and for even parity. So let's discuss how we can design parity generator and parity checker for even parity and for odd parity. So let's discuss one by one. 3-bit even parity generator. Consider a 3-bit message to be transmitted together with an even parity bit. The 3-bit XYZ constitute the message and are the inputs to the circuit. The parity bit P is the output. For even parity, the P bit must be generated to make the total number of ones, including P, even. So how we can do this? So 3-bit even parity generator. Here we have a truth table for this even parity generator. For 3-bit message XYZ, we have a total 8 possible combinations. So here we write this 8 possible combination for XYZ 3-bit message. Now consider first combination XYZ 000. So here number of ones 0 time, that means for even time, so P must be 0. Then for 0, then 3-bit message 001, here number of ones 1 time, that means odd time. So to make this count even, we have to add another 1. So we consider P as a even parity for P is equals to 1. So here we have a parity bit 1 for combination of 001. Again for 010, number of ones 1 time. So we have to add parity bit as a 1 to make count number of ones even time. Then next 011. So here number of ones 2 time, that means even number. So P is equals to 0. Then 100, number of ones odd time, so P consider 1. Then 101, number of ones 2 times, so P is equals to 0. Then 110, so here number of ones 2 times, so P is equals to 0. Then X, Y, Z, 1, 1, 1. Number of ones 3 times. That means odd count. So we have to add P is equals to 1 for even parity. So this is how we can make a truth table for this 3-bit even parity generator. Now let's calculate logical expression for this P bit by K map. So here we have a 3 variable K map for X, Y, Z condition and write this P bit over here according to the combination of X, Y, Z. So here we can't make a group. So we have this P equation X dash Y dash Z plus X dash Y Z dash plus X Y dash Z dash plus X Y Z. We can simplify this logical function by converting this logical function into XOR form as this x dash y dash z plus x dash y z dash plus x y dash z dash plus x y z is equal to x XOR y XOR z. So how this can be converted into XOR? So here procedure for conversion of this equation into XOR. First, rearrange this equation, then take z bar as a common from this first and second term and z from third and fourth term. So here we have a equation of XORing and here equation of XNOR, which is can be written as a x XOR y bar. And again we have this equation x XOR y XOR z bar plus x XOR y bar z, which is considered as a b dash a dash b, which can be written as x XOR y XOR z. So here we have a logical diagram for 3-bit even parity generator x, y XORing then z XOR. So we have a parity bit. So here we have a 3-bit even parity generator using this logical diagram. Now let's discuss about 3-bit odd parity generator. So consider a 3-bit message to be transmitted together with an odd parity bit. The 3-bit X, Y, Z constitute the message and are the inputs to the circuit. The parity bit P is the output. For odd parity, the bit P must be generated to make the total number of ones including P odd. So let's discuss truth table here. X, Y, Z, total 3-bit message. So we have 8 possible combinations. Now make these possible combinations or says make this message odd parity bit message. So here for first combination 0 0 0 we have a number of ones 0 time, that means even. So we have to add parity bit P is equals to 1 over here for number of one count odd time. So we have a 0 0 0 1. So total message contain number of ones 1 time odd parity. Then 0 0 1. So number of ones 1 time odd number. So 0. Then again odd number. So 0. Then for 0 1 1 number of ones 2 times. So here we have to add P bit is equals to 1 for odd count. Then again 1 0 0. So number of ones odd times. So P is equals to 0. Then 1 0 1 number of ones even time. So we have to add P is equals to 1. Then 1 1 0 number of ones 2 times. So P is equals to 1. Then 1 1 1 number of ones odd times. So P is equals to 0, which is exactly complemented of this even parity. Now we have a K-map over here and logical expression. This logical expression can be deduced into this form. According to this, P is equals to x dash y dash z dash plus x dash y z plus x y dash z plus x y z dash. This equation can be converted into this form x XOR y, and this x XOR y can XNOR with z. So this is how we can generate 3-bit odd parity generator. Here we have a logical diagram for odd parity generator. X and Y XOR, then Z XNOR. So we have a 3-bit odd parity generator. Now let's discuss about parity checker. The 3 bits in the message together with the parity bits are transmitted to their destination, where they are applied to a parity checker circuit to check for a possible error in the transmission. The information was transmitted with even or odd parity. The 4-bit received must have an even or odd number of ones respectively. As we have a 3-bit message plus 1 parity bit, so at the receiver side total 4 bits received. An error occur during the transmission if the 4 bits received have an odd number of ones for even parity and even number of ones for odd parity, indicating that 1 bit has changed in value during transmission. The output of parity checker denoted by C checksum will be equal to 1 if error occurs. So here let's discuss about 4-bit even parity checker. So here we have a table. We have a total 4-bit received X, Y, Z, P bit. So for 4-bit received over here, we have a total 2 raised to 4, 16 possible combination. So for this 16 possible combination, we have to check that in this message there is a even parity or not, and if there is no even parity, then C is equals to 1. For example, for X, Y, Z, P, we have a 0, 0, 0, 0. That means number of ones 0 time, even time. So no error. So C is equals to 0. Then 0, 0, 0, 1. Number of ones 1 time, that means odd time. That means there is a error. So parity check bit C is equals to 1. Then for 0, 0, 1, 0. Again number of ones 1 time. That means odd time. So C is equals to 0. Then for X, Y, Z, P, 0, 0, 1, 1. Number of ones 2 time. That means no error. So C is equals to 0. So this is how we can check this 16 possible combination and write C is equals to 0 or 1 according to number of ones present in this message X, Y, Z, P. If number of message even time, then C is equals to 0, and number of ones odd time, that means error, then C is equals to 1. So this is how we can calculate this parity error check bit C, and now we have a K-map for this C bit in form of X, Y, Z, P, total 4 bits. So we have a 16 possible combinations. So here we have a K-map for this combination. Now here we can't simplify the logical function, but this shows that we have a logical function of C as X XOR Y XOR Z XOR P. Here for even parity checker, we have a equation of C X XOR Y XOR Z XOR P, which can be implemented over here as XY XORing, ZP XORing, then again we XOR output of this logical gate. So we have a C bit which has a logical expression X XOR Y XOR Z XOR P. So this is how we can generate parity checker bit for 4-bit even parity. Next, discuss about 4-bit odd parity checker. So here we have a table for 4-bit received X, Y, Z, P. Here we have to check for number of ones odd time. So here whenever number of ones odd time, then C is equals to 0. Otherwise for number of ones even time, we have to make C is equals to 0. For example, for 0, 0, 0, 0, 1, number of ones 0 time, that means even number. So this can be represented that here error generated. So C is equals to 1. Then 0, 0, 0, 1. In this message, number of ones one time, that means odd time. So C is equals to 0. Then 0, 0, 1, 0. Number of ones one time, that means odd time. So here C is equals to 0. Then 0, 0, 1, 1. Number of ones two time, that means even time. That means here we have a error over here. So C is equals to 1. So this is how we can calculate 4-bit odd parity using this total 16 possible combinations. This odd parity table and even parity tables are exactly opposite of each other. Here we have a K-map for this C bit. We have a total 16 possible combinations. So according to that, we have a K-map over here for 4 variable X, Y, Z, P. And as this even parity and odd parity are exactly complemented of each other. So we can write this C equation as X, X or Y, X or Z, X or P bar over here. So this is how we can calculate 4-bit odd parity check bit, and we can implement this equation over here XY XOR ZP XOR, then again XOR, and then invert this. So we have a C bit for 4-bit odd parity checker. So this is how we can implement 4-bit odd parity checker circuit. In this session, we discussed about parity generator and parity checker circuit for even parity and for odd parity. Thank you.